Myung, thank you so much. I'm sorry for scheduling you so much at Minnesota. I'll be careful next time. I feel I overscheduled you, but you were very popular.
Oh, I love that.
You were very popular. I want to make sure before I get started I clean my glasses with my KAIST branded material here. I don't know who this is, but I could have got a chemistry version of this as well, I think. I am so happy to be here. I was happy to be here in 2019 because it was part of a nice symposium with other colleagues, and I've had such a strong connection with Korean scientists over many, many years. And when I look out in the audience, it makes me feel like I'm in Minnesota with all my ex-Minnesota folks who have spent time there in different groups and including my group. So it's really wonderful to be here. And I also want to say that, Myung, thank you so much for hosting both me and I'm joined this visit by my wife too. I asked her if she wanted to come to my lecture. She said no. And she's been treated so well here, and so it's been just a wonderful visit. I feel very kind of close connection, and it's the record for the biggest sign advertising my lecture ever over there. Somehow I want to get that home to Minnesota. Also for those of you who have seen this lecture before, I put some new slides just for you. So
thank you.
And you can make, and I'll do a better job than last time. I will try to do a better job than last time. So you heard that I'm interested in sustainability. My entire group works at the intersection of sustainability and polymer science, which is really important to me, and I think it should be important to you. That's the theme of this lecture. And although you'll probably clearly understand all the words in this title, I will come back and say why I think the materials that I'm presenting to you today have some remarkable characteristics that both emphasize properties of materials but also end of life. But I want to talk not about science in the beginning, because a lot of times I get feedback about sustainable polymers that this is not a science and technology problem. This is a policy problem with waste. And you might remember in 2010, it was reported that there are estimated 8 million tons of plastic waste in our oceans. And that was really sparked everybody's interest in what is happening with all this plastic waste. And this article a few years ago in Science argues that if we continue as business as usual, this number of so-called plastic emissions could, increase by maybe up to a factor of 8 or more than those 2010 emissions. So we have to do something about this, and even if we have ambitious kind of targets to get back down to those 2010 levels requires serious intervention. And politically, I think the policies that need to support this are reducing or eliminating unnecessary plastic, setting global limits for new plastic, making materials that are recoverable or recyclable, and thinking more about recycling in general. And they argued that for high-income countries like South Korea, Japan, United States, that we need to have ambitious targets of reducing our waste by 40%, effectively managing 99% of it, and recovering the annual 40% of annual emissions. And these are much harder for low and middle-income countries. So we have a huge problem on our hands. And you can I think in December, these folks made a simulation about how, and this is not my expertise, but they simulated how policies could change the outcome. And just as how we use plastics, most of how we use plastics are in front of you today in packaging, construction, textiles, and these applications. And this is where they end up. The majority end up in landfill. They're incinerated, which can have negative air pollution effects. And recycling is growing, pretty big chunk, but nowhere near as big as these. And this is the problem one. It's mismanaged. Because mismanaged plastic waste leads to environmental, ecological, and human health damage. And that's what we want to try to change. And these folks argued through policy that you could change this. You could reduce the amount of mismanaged waste by 90%, primary production by 60% because of using this 4 policy package I'll talk about in a minute, and even lowering greenhouse gas emissions. So there are many articles like this. I like to keep up with this and pick recent ones that kind of are at the forefront of policy. They argue that if you have a policy that requires recycled content, you cap primary production, invest in waste management investment, and have a plastic packaging tax, that this could be accomplished. That takes political will. In the United States of America right now, we have a problem with political will, okay, that I am living every day. Because sustainability is not at the forefront of the current administration's mind in global climate change, et cetera. This is a very difficult situation to be in. However, with sufficient political will, there's enough technical potential, things you work on, things we work on, to substantially reduce mismanaged plastic waste. And I think that's what we should all be kind of, concerned about. It's managing the waste, because plastics are so useful in everything we do every day. And that's the dilemma. The UN is worried about this. They have an intergovernmental negotiating committee about how to turn off the tap of plastic pollution. And it's compelling that have their hands in the most significant opportunity to turn off the tap and solve plastic pollution. I hear talks about the only way to do it is improve recycling. The only way to do it is reuse materials. The only way to do it is reduce materials. And I'm here to say that, in my opinion, we need many, many solutions. One size will not fit all. We need many solutions in this problem. One they recommend is in the area of degradable plastics, and that's what I want to talk to you about today, more specifically about composting. And composting I'll tell you about in a bit, but innovation on new materials that are bio-benign, ephemeral, short-lived, lower cost, and/or are coupled to available waste infrastructure for zero leakage is a key recommendation from this UN report. And I believe that that will ultimately be a piece of the plastics puzzle. It will not be the solution for everything. So, when I talk about degradation, I want to be careful about using the word biodegradable. In fact, in the state of California, you can't label products as biodegradable. It's illegal. And the state of Minnesota is adopting a similar law. Because biodegradation depends on not only is the plastic degradable, but where does it end up? Does it end up in the ocean, industrial compost, landfill, the campus of KAIST? We have to identify both the environment and the plastic. And this is a nice article that talks about both characterizing the biodegradable plastic and the environment, understanding mechanistically what happens when the plastic is degraded. It doesn't go away. It's converted into something, and how that is done is important to understand. So it will not be the only solution, I agree with that. And one of the areas that I'm interested in is composting. It's a natural process that turns organic materials into a valuable soil amendment. Compost has a unique ability to improve chemical, physical, and biological characteristics of soil. Maybe you've composted or tried to at home in bags. I went to Cricht yesterday, and I saw they have compostable plastics made from PBAT, polylactide, and other degradable polymers. But if you live in Minnesota, you can get your stuff to compost. So this is actually in the southern end of Minnesota. This is food waste, pizza boxes, compostable plastic bags, and you'll notice one thing in there. We went right around early November. There are a lot of pumpkins. That's after Halloween. So pumpkins are compostable. So we went to this place and looked at all this material, and they do a general chemistry stoichiometry experiment at this composting facility, because to get proper compost, you need the right amount of nitrogen-carbon ratio. And that depends on putting leaves and twigs and grasses, and they mix it and they get it just right, okay? And that's how they start the compost. This is in the alley of a Minneapolis home, not my home, but my home looks almost exactly like this. I have 3 bins. I can put PET bottles here. I can put other waste that'll be incinerated here, and this green one is for food waste and products that are certified compostable, industrially compostable. So forks, cutlery, plates, that kind of thing, packaging that's certified compostable can go in there, and this facility takes them. All right, this is literally outside my office, so the University of Minnesota has infrastructure that we can use for compost. It gets turned into this pile of dirt, and this pile of dirt they sell. So it's not a high-value product, but it's a product with some value. So converting waste into a valuable product is a way to divert it from landfills, and with the proper infrastructure, we can help part of that mismanaged waste. Okay. The problem is there's only 200 food waste composting facilities in the US, and only a fraction of them accept compostable food contact packaging. And they're worried about contamination because that polymer there looks a lot like the compostable polymers I'll tell you about today. So education is a big part of this. And when they sell their compost, they don't want microplastics in it. They don't want garbage in it. So this is a big policy issue as well. It is contaminated. This study showed that it is contaminated. There are some plastic films and plastic cups and things like that, and rocks and glass and metal. But there's about 22% compostable packaging in a typical compostable facility that takes compostable packaging. Moreover, the takeaways are that if it's certified compostable, it's pretty much compostable. They fully disintegrate, but widespread adoption requires collaboration, labeling, and understanding education about this. This is the Compost Council and the Compost Consortium in the US. Okay, so to me, that's a really potential solution, but infrastructure is not big yet, but it's growing. In fact, another composting facility in Minnesota has just tripled their capacity, in large part because of the prevalence of more compostable packaging. You know this polymer, polylactide, I'm sure. It's an aliphatic polyester that's kind of like polystyrene in its physical properties. It's a rigid, brittle thermoplastic, high-strength thermoplastic. What you might not know is that a chemist called Pat Gruber earned his PhD in carbohydrate chemistry at the University of Minnesota in the late 80s. He went to Cargill, and they told him, could you do something with lactic acid other than put it in food? So he looked at industrial uses of lactic acid, and he recognized that you could make polylactic acid, which was a biomedical material for sutures and things like that. And the very first person to polymerize lactide, do the ring opening polymerization of lactide in the literature, was a JACS publication in 1932 by a famous polymer chemist called Carruthers. You can look it up. He heated up lactide to 250 degrees Celsius with potassium carbonate, and he got polymer. We do things much more controlled these days. But that you could take the cyclic dimer of lactic acid. This is lactic acid doubly dehydrated. Lactic acid comes from the fermentation of renewable sugars. You can convert that cyclic ester into a polymer by ring opening polymerization with any number of acid-base organometallic catalyst, organic or organometallic catalyst, and almost any alcohol will initiate it, and that means you can control the end group here. That's going to be important for my talk. I've given you one enantiomer of lactide. The other enantiomer is commercially available, and the meso compound is also commercially available. So these are commercially available molecules that make plastics that you've probably used. In fact, the infrastructure at University of Minnesota is there because all of our plastic in the food, in the student services, student cafeterias is PLA. So we have an outlet for the composting of that at the University of Minnesota. So these other applications as well. Global production is about 1 million metric tons. That's small. That's 1/10 of the amount of plastic in the ocean. Okay, so that's a small amount every year, but it's growing. It has a combined annual growth rate of about 20%, which means its estimated value in 2020 is about $3 billion. This is a polymer I'm going to tell you a lot about because we like this polymer and we think there's opportunities to expand its utility. When we think about sustainability and polymer science, however, we think about it in 4 main pillars at the University of Minnesota, which I would encourage you to think about in your own projects. Where did my monomer come from? My cyclohexene. Where did it come from? Okay, and what is its origin? Is it renewable? Is it a waste product? Is it whatever? How do I make the polymer? Do I use catalytic processes? Do I use energy efficient processes? Do I have waste prevention? I'll talk about all of those things. How good is it when I want to use it? Okay, is it have competitive properties? And one that's often ignored is the economic viability. Also very important in plastics because all the plastics you see in front of you are basically free. They don't cost anything. They're very low cost materials. And then finally, what happens at the end of life when you put it in the compost bin or you degrade it or reprocess it? I'm going to focus on polylactide block polymers. And we just had a paper that was accepted in Biomacromolecules, not even updated yet, that talks about this format. So we used a long squiggly line for a polymer. This is an A, B, A tri-block polymer. I'm going to focus on how PLA block polymers, we argue, are versatile materials for sustainable future. And that's where I'm going to now narrow down and tell you why I think block polymers are a potential solution. The reason I think they're a potential solution is because I argue that block polymer strategies, which combine the properties of two types of macromolecules, two or more types of macromolecules into a single component material, offer unparalleled control over macromolecular properties through microstructure, molar mass, morphology, composition, and architecture. I'll touch on all of those today, actually. And I'll argue that, like any homopolymer, one simple polymer, there are limitations. You know, its melting point, its glass transition temperature, its toughness. I already told you it's a brittle thermoplastic. We want to address those limitations, retain the environmental benefits of polylactide, renewably resourced and compostable, expand its applications, and on the way discover new materials. Now you might think block polymers are exotic and academic curiosities, but they're actually item of commerce. They're used in toothbrushes, running shoes. All your cars have block polymers in them. They're about a $14 billion industry. Kraton, the styrenic ones, are the most common one, where styrene is combined with polydienes like polybutadiene and polyisoprene. So our goal is to take polylactide as the red block and put it into block polymers, and the simplest ones here are either with low composition of the red component or high composition of the red component. And what I want to tell you about, it's a pretty simple molecule of the blue component, but we're going to take a holistic view on the blue component using those pillars of sustainability that I told you about. So this is a simple molecule called methylcaprolactone. It's gamma methylcaprolactone. It's a racemic mixture of this molecule. It's just a substituted caprolactone. Caprolactone is a commercially available molecule. So if you take the same kinds of catalysts and initiators that we did for lactide, you can make this aliphatic polyester that has a glass transition temperature of -60, and this methyl branch leads to an atactic methyl branch leads to an amorphous material that can't crystallize. That turns out to be important for elastomers, because you don't want elastomers when you're doing recovery experiments to crystallize. So that one methyl group plays a nice role. But I want to tell you about how we make block polymers using this, how we can think about where this molecule could come from, and where does it go at its end of life. And we've been working on this for a long time, and I think we've actually hit upon a really attractive candidate for a soft block, they call it, in block polymer materials. So the work that started us off on this was by Annabelle, and Annabelle earned her PhD in 2018, and in 2017 she published this paper in Biomacromolecules that took methylcaprolactone, a simple diol initiator, and simple tin-based catalyst, and she was able to make polymethylcaprolactone that had a hydroxyl at each end. You can add lactide, in this case it's L-lactide that we added to make the ABA triblock, and that chemistry is highly reproducible and easy to do. I'll show you the same chemistry scheme probably 6 times in this talk. It's easy to stitch these molecules together that way. They self-assemble into nanostructures like most block polymers do that have incompatible segments. Typical ones that I'll tell you about have isolated domains, spherical or cylindrical, of one component embedded in a matrix of the other component, and that's really important for block polymer properties. Here are stress strain curves of what she made. This is stress as a function of strain in a tensile bar. If you take 80% lactide, that's a high composition of lactide, you make a rigid and ductile thermoplastic. If you take 20% lactide, you make an extendable elastomer that doesn't break until over 10 times its original length and has a high tensile strength. We did recovery experiments, and this is going to be an important point. The L-lactide can be atactic and amorphous. It can be isotactic and amorphous because it's a slow crystallizer, okay? And you can also make it semi-crystalline. If it's important in elastomer recovery experiments that the end block is semi-crystalline, that you use an antimerically pure lactide, commercially available, and you let the material crystallize. If you do that and you pull the elastomer, rubber band, and you let it recover, you have pretty small amount of residual strain in the material. So when you pull a rubber band and it comes back, it basically comes back to its original length. You don't want to pull a rubber band and have it be loose and extend and have permanent deformation. We also look at that through stress relaxation experiments, and this is when you pull the rubber band, the elastomer 10%, and you ask how much stress does it take to keep that extension, and the stress decays depending on the temperature. So at low temperature, it decays slowly. At high temperature, when the domains are becoming rubbery, you lose all that stress. So at 50 degrees, these are not great elastomers. But when you use the semi-crystalline variant, we have very nice stress relaxation behavior, and you see these materials retain their stress. So we know that the end blocks have to be semi-crystalline. Annabelle went on to really characterize this system very well. We know that they self-assemble by small angle X-ray scattering. We know their rheological profiles. We've estimated the entanglement molecular weight and the Flory-Huggins interaction parameter by looking at the order or disorder transition temperature of these materials. We have a lot of flexibility in these materials, and she got us basically up and going on this gamma-methyl caprolactone. Reminder, the TG of the blue block is -60, the TG of the red block is 50. You can make the red block semi-crystalline, it melts at 170. This is pretty cool. You may or may not know that if you take right-handed PLA and you mix it with left-handed PLA, you make a stereo complex that has a high melting point of 220 degrees Celsius. We're going to take advantage of that in this presentation. And we, like I said, we have the entanglement molar mass and the Flory-Huggins interaction parameter. So we love this molecule, and we love this polymer. Where could you get this molecule from? So for the organic chemists in the audience, do your own retrosynthetic analysis. Probably you know how caprolactone is made. Does anybody know how caprolactone is made? I always, you know how styrene, you know, all the kind of common monomers, I try to encourage people to figure out where they came from, if it's exotic cyclohexene or styrene. Well, one of the ways, the most predominant way to make caprolactone is from phenol, actually. So we're interested in bio-based resources to get to phenolics, and lignin is a candidate. There are many chemists around the world trying to turn lignin into money, and it's very hard because lignin is free, but it's really a complex mixture of stuff. But if you do these what are called catalytic fractionations, you can start to get monophenolic mixtures. In fact, the most predominant one is propylphenol, okay? But you can also get cresol, para, meta, and ortho-cresol, which is methylphenol. Okay, so with methylphenol, probably you quickly see that you could make methyl caprolactone because the hydrogenation of cresol gives cyclohexanol, the oxidation gives cyclohexanone, and the bioavailable oxidation gives methyl caprolactone. So what my chemical engineering colleagues did was they said if, and this is kind of a big if, you could probably get cresol for $1 a kilogram from coal tar, but if you could get it from bio-based resources for $1 a kilogram, by the way, it can come from other things like cellulose, lignin, and cellulose and terpenes, is that they did the unit operations of hydrogenation oxidation and then a second oxidation, and they estimate that you could probably buy methyl caprolactone for $2.50 a kilogram. And as I've always said, this is not the cheapest polymer you'll ever buy, but it's reasonable. We never did this chemistry on scale, but we estimate that's what it would cost. So one of the issues is from lignin, you would not necessarily get pure para-cresol, number one. And number two is if you can avoid the hydrogenation step and go directly to converting the phenol to the ketone, you would save a step. And that's what's happening now. I don't have the reference. This is 2025 paper. My colleagues are looking at how you can do selective hydrogenation of cresol to give the ketone directly. And these are zeolite chemists who work very hard on trying to engineer zeolites to do the selective chemistry, and they end up making 80% conversion of these phenols and over 90% selectivity to the ketone with para-cresol. Like I said, there's also meta and ortho, less impressive in the ortho, but these mixtures could be utilized to make these monomers. And the other thing is if you have mixtures, then you would get mixtures of methyl caprolactones. You'd get gamma, beta, and delta. You get epsilon as well. And so what Derek looked at was taking these mixtures and doing the controlled polymerization. This is Mn, molecular weight versus conversion. They all behave the same. In fact, the blue one is a mixture of all three monomers. The dispersity is understandable. The kinetics are all about the same. I guess you would predict that because the business end of the molecule is the ester, and all of those esters are pretty unencumbered by the methyl group. One of the other things that he looked at, though, was he's using acid catalyst, and these are two kind of common organic acid catalysts. They go through what's called an activated monomer mechanism. The monomer is protonated, and then the exogenous nucleophile attacks the intermediate protonated ester. He looked at this volatile catalyst, DMP. It has a boiling point of 174 degrees Celsius. So if you put that, if you take your monomer, pure, no solvent, and you add the catalyst to that, at 100 degrees Celsius, in about an hour, you'll convert almost all of the monomer. What he then did was he used reduced pressure to remove the residual monomer, that's these resonances here, and he also removed the catalyst. So now you've got a pure polymer ready to go for the next step, no solvent, no precipitation, in what is, could be translated to an industrial type of process. Moreover, you've collected the catalyst in the other flask, and you can use it again. So that's a green chemistry kind of process advantage that you can have in these acid catalyzed systems. For those of you that recognize that when you heat it up and you pull vacuum and you pull off monomer, if there's still catalyst in the reaction, the catalyst will catalyze the depolymerization as well. Okay? And you'll lose molecular weight. So if you use a non-volatile catalyst, you start to depolymerize. So you have to use a volatile catalyst in order for this to work, because you have to remove the catalyst so it doesn't depolymerize. So the most volatile catalyst, acid catalyst that we can think of is HCl. So we started pursuing that. I'll tell you about that in just a minute. When you do make these polymers, you end up making materials that have similar rheological properties. So we argue from polymerizability and from a materials property standpoint, there's no difference. You can get away with a mixture. Typically, we don't like using mixtures in our science, but here's an example of where I think it could be an advantage. Endo in 2000 showed that you could polymerize cyclic esters like caprolactone with HCl. You can go to Sigma or your chemical company and buy HCl and ether. And in fact, Jacobson had a really interesting paper recently on catalysis with HCl goes to the oxonium ion, actually. It's really kind of fascinating to me. And we were motivated to try HCl in our polymerizations, because even with valerolactones, they're very active at low temperature. So what Marianne did was she took methyl caprolactone, this initiator, HCl and ether, no solvent, neat monomer, able to easily make this polymer, pretty good kinetics, activated monomer mechanism. But what this allowed her to do was mix that monomer with this monomer, which is a difunctional methyl caprolactone, if you will. That cross-links the material, and you make a cross-linked thermoset in situ. Because you mix the monomers, it's a liquid, you add HCl and ether, the thing polymerizes to make a thermoset elastomer, and then you let it evaporate, that's it. There's zero catalyst residue. So the catalyst that was doing the work is easily removed even from a solid material. And you can see that by this temperature-independent modulus of the material. So that's a convenient way to do it. We've been studying this more. Simran in our group is looking at the kinetics. We have a very simple rate law, first order in HCl, first order in initiator, and we have a temperature dependence. And first order in monomer, we have a temperature dependence. It gives us that activation energy for a 6 kilogram per mole target. We are modeling this with the so-called activated monomer mechanism, and this is a paper in Macromolecules that talks about how the kinetics and mechanism are influenced by catalyst concentration in the presence of esters in the monomer in the polymer. We have a molecular weight limitation right now we can't figure out, but we're on it, and so hopefully we can solve that problem with understanding the fundamentals of how this works. I want to interject our latest work, because methyl caprolactone and its mixtures are one kind of polymer, polyester, but if we make the ketone, we can also turn it into the cyclic amide. So we made this caprolactam. By the way, nylon 6 is a huge polymer. You know about it. That's from the polymerization of caprolactam. So we made methyl caprolactam. This is also an activated kind of monomer mechanism where you deprotonate the amide with strong base, and this activator starts the polymerization. So we looked at copolymers of methyl caprolactam and caprolactam. I'm not going to tell you too much about it other than the applications we looked at were additive manufacturing, 3D printing, and hot melt adhesives, and they behave beautifully there. It turns out there's a really interesting phenomena though, because the methyl caprolactone is non-crystalline and more hydrophobic. The caprolactam polymer is crystalline and less hydrophobic. And so there's an interesting humidity response of these materials. We make incredibly strong materials, so there's methyl caprolactam, the dotted line here, and you know, they're tensile strengths of over 60 megapascals. And in humid environments, these tensile strengths are incredibly high. And we think that this really steep slope in the stress strain curve is because we're having stress-induced crystallization that really strengthen the materials in the copolymers of caprolactam and methyl caprolactam. So we're trying to do everything we can with methyl cyclohexanone because we want to make people understand the potential of these molecules to make them even more attractive for others. The other thing I want to point out, because it really got us, it'll connect into the next section, is that these polymerizations are so easy to do, and you can use the power of protecting groups in organic synthesis to make some really interesting architectures. And we recently published the preparation of H-shaped polymers. This is a different type of architecture. It's a homopolymer, all the same monomers, but the molecule is shaped like an H. Back in the macromolecules, by the way, all the references are macromolecules. Back in macromolecules in 1981, people made polystyrene H-shaped, and in 2022 or something like this, people were still using those same molecules to understand the rheology of these polymers. Hard to make H polymers. With lactide, we recognized that taking chemistry that was from others as well, is that if you end cap the polylactide with this protecting group here, this acetal, you could carefully deprotect with trifluidic acid and dichloromethane to generate 2 hydroxyls at the end of the polyester on this end and 2 hydroxyls on that end, and that ends up allowing you to make the H polymer. And the moldy mass spectrum is really beautiful of this. We can see the protected version and we can see the deprotected version. So based on chemical information and on rheological analysis, we're confident these materials are actually H-shaped, which have really interesting flow properties because of their architecture. Okay, so let's go back to block polymers, take advantage of architectural control, and show that now if we want to stitch together the red and blue, we can do it in all kinds of ways. Annabelle did the basic red, blue, red. What if you wanted to put red hanging off of blue? And people do this all the time to make graph polymers. So what Lucy did was she took this ketone initiator with a hydroxyl group, grew off polylactide that had a ketone at one end. She capped the hydroxyl group with an acetate. She oxidized the ketone to give the cyclic ester, and then she copolymerized this macromonomer with methyl caprolactone to make this kind of architecture. So this is a way to stitch polylactide chains along the backbone in an all polyester block polymer. That hasn't been done before. It's usually a hydrocarbon backbone in polylactide grafts and bottle brushes, but we're able to do it through manipulation. Again, the MALDI is beautiful. That shows step by step going from the hydroxyl to the acetate to the cyclic ester, and the simple change in the MALDI mass spectrum. We stopped studying that polymer from a property standpoint. It's a little complicated to make and kind of de-emphasizes my point about how simple it is. This is really emphasizing the power of polyester synthesis using simple catalysts and simple organic manipulations. But what we did do was build on a paper of macromolecules, I told you, in 1976 that looked at star polymers. If you want to make stronger elastomers that are more resilient, that are more easily to recover, you can change the architecture from linear to star. This is pretty well established in the literature. Most recently, Burns and Register showed that if you made star polymers of polyolefins, they had increased strength and improved recovery over the linear analogs. The reason that's argued in the literature is that when you pull a material, if the hard block comes out of its hard domain, then the polymer that's connecting the hard domains is no longer elastically effective, so it's not contributing to the cohesion of the material. But in a star polymer, there's a permanent crosslink at the core. And if you do pull out one chain, all these other domains are still interconnected through the one, I'll call it permanent crosslink. In PLA, block polymers, this is trivial. Don't use a diol initiator, use a 4-alcohol initiator. Now you grow from a central core and you end up making either a 4-arm star or a 6-arm star. Simple, straightforward chemistry to do it. You just change from diol to tetraol to hexaol. So what Stephanie did was she made these, and every time we made a star polymer, the tensile properties outperformed the linear. Higher stress at break and just as long elongation at break, by a lot. I mean, 10, 20 megapascal difference. Now this molecule is half the molecular weight of this molecule, and this molecule is 3 times the molecular weight of this. So when you're comparing the linear to the star, you have to ask yourself, is it just a molecular weight effect? Then now we have higher molecular weight and they're stronger. That's normal in polymers. When we made polymers that were the same molecular weight, linear and star, again, the stars outperform. Same molar mass, stars outperform. A simple change in initiator structure leads to a dramatic change in architecture and ultimate performance. So now we're like hyper-focused on stars because they are comparable to commercial materials, the cratons that have a $14 billion industry. Ultimate tensile strength, strain at break, and percent recovery. And there's Stephanie, and she showed that these are really kind of competitive molecules. Now, I don't like to highlight the deficiencies of my own work, but I will do it now. PLA is very slow to crystallize. So you have to process these materials in the following way. You have to make a compression, compress them into a plaque, and then you have to wait at lower temperature for the PLA to crystallize in order to achieve these properties. That's not great. That's not great. So what Maggie did recently was she started to build on the star architecture, but now I'm going to go back to what I introduced before by making the 3-arm star, sorry, the 3-component star with PLLA, right-handed PLLA, and left-handed PDLA. The orange and the red can now make a stereo complex. I told you that it has a higher melting point because of increased van der Waals interactions in the crystal structure, but it also has a really rapid crystallization rate. So you get 2 benefits, higher thermal stability and rapid crystallization. And she does it by the same chemistry. You add lactide of this enantiomer, you add the other enantiomer, and you can make the triblock-like structure. I'm going to show you what the difference is when you make this small change. Remember, it's a star polymer with polymethyl caprolactone and polylactide at the end. That's the same. The only thing the difference is the enantiomeric versions that you use. So if you use the homopolymer PLA and you use just lactide with no stereocomplex formation ability at all, I'm going to highlight that problem with crystallization. At low temperature, you go through the TG of PMCl, that's room temperature, that's the TG of PLA, then you heat and the modulus increases. The modulus increases because it crystallizes upon heating. So the hard domains are starting to crystallize, they're higher modulus themselves, and they contribute to the overall modulus. The PLA melts at about 160 degrees Celsius, and then you ultimately get terminal flow. So look at all the other ones. All the other ones have the ability to make a stereo complex. You see several things. You see the TG is the same, and then you see that the, oops, sorry. It took me an hour to make this, so you can watch it again. You see that the room temperature modulus is controlled by the amount of stereocomplex ability you have in the polymer. But look, once you get past the TG of PLA, the modulus stays the same when you heat. There's no crystallization, and the flow temperature is much higher. So by that one change of stereoisomer, you really dramatically change the properties. And we know how to control now the ultimate tensile strength and percent recovery. But look at this stress relaxation data. This is when you make the stereo complex. Very good stress relaxation performance, I would say. It doesn't relax much stress over the experimental time frame, even as high as 120 degrees Celsius. This is 70 degrees, 60 degrees above the TG of PLA. So the crystallinity in the hard domains is making a big effect, okay? I don't know why. Myung asked me after my seminar why. I don't know why exactly. I wish I understood more about it. Here's a hypothesis. The hypothesis is by changing the relative length, I don't know why we changed colors here from blue to pink, I don't know. Anyway, by changing the relative length of the stereocomplex crystallizing component, you control where the stereocomplex is relative to the polymethyl caprolactone interface. So interfacial phenomena at the block nanoscopic level could be contributing to the overall mechanical properties of these materials. And I don't know, I can't tell you more than that now because I don't have any more experimental evidence, but we do think that's the part of the origin. And the effect is actually pretty interesting because the modulus of room temperature changes by over an order of magnitude depending on the sequencing of those blocks. All right. I'm going to remind you about propyl caprolactone because I want to tell you about Michaela's work. So propyl caprolactone gives propylphenol gives you propyl caprolactone. We made a different kind of polymer. In this case, it's a polyurethane urea. And here is polypropyl caprolactone, a oligomer about a few thousand molecular weight, and you make a polyurethane urea that has outstanding mechanical properties competitive with BASF product called Elastolan. So nobody is surprised by that here, probably. We wanted to use propyl caprolactone because it's got this connection to lignin. And turns out, believe it or not, nobody had polymerized propyl caprolactone before. Actually, I don't even believe it myself. Probably somebody in the patent literature did it at DuPont. But we looked at the thermodynamics of this polymerization and learned that it has an enthalpy of polymerization that's actually bigger, almost statistically bigger, than methyl caprolactone. That means the propyl version enthalpically is more driven to the polymer. Delta H of polymerization is more favorable. But the entropy of polymerization estimated by this Van Hoft analysis says that the entropy of polymerization is less favorable. Okay? And this is going to be related to what I talked to you about earlier in terms of rotational degrees of freedom and estimates of entropy of polymerization, which are related to your thermodynamics as well. But what that means is that you estimate the sealing temperature of this polymer, of this monomer, is about 1,000 degrees Celsius, and this one's 361. The sealing temperature is the temperature above which you can't polymerize the monomer because it's thermodynamically impossible. Nobody's going to heat this monomer to 361 degrees Celsius because you'll basically destroy it. But it tells you that it's easier to depolymerize when it's in polymer form. So we heated our polymer up to 250 degrees with a catalyst in it. We recover 4-propyl caprolactone in very high purity by GC and by NMR. This gave us the motivation to take those polymers and put them in an extruder, a commercially viable polymer processing technique, and hook to the extruder reduced pressure possibilities. So we could pull vacuum on the extruder, and people do this. This is not so fancy. Devolatilization is a classic example of that. And we're able to to depolymerize the polypropyl caprolactone. We use linear low density polyethylene as a kind of process aid. We use an insoluble Lewis acid catalyst. At 160 degrees, we get very high purity propyl caprolactone back, selectivity of 100%, and yield approaching 100%. So now you could feed your plastic into an extruder and collect the monomer, make new plastic, and go around the loop. And that is much more tractable with propyl caprolactone than with methyl caprolactone. So there could be some interesting advantage of using the propyl version, which we didn't know until we studied the thermodynamics of polymerization. Here's one application where you could use these block polymers. I showed you pictures of running shoes, toothbrushes, or told you toothbrushes, car parts. Here's an example of using it as a pressure-sensitive adhesive. We've been working on this for a long time in different kinds of polymers. But if we take these tri-blocks that Annabelle made and we mix them with a commercially available tackifier, we can look at the small angle X-ray scattering and differential scanning calorimetry. Tells us that the tackifier is easily mixed with the mid block, and we still preserve the nanostructure even at high fractions of tackifier. We have to process these by solvent. That's not great, but when we do that, we end up with rheological properties that end up being good for a pressure-sensitive adhesive. You have to have flow under light pressure, and then after you let go, you have to have good cohesive strength so that the paper stays on the wall or whatever. And we estimate that these should be good high shear strength PSAs with good substrate wetting abilities. In fact, they're like electrical tape or office tape in terms of peel strength or loop tack, and they have very good shear strength. If you take the polymers, and this is a preview of the end of life, and you expose them to strong base, those esters hydrolyze. In fact, the black data is our polymer itself, and after several days, several weeks, it basically fully hydrolyzes. The taggifier is more hydrophobic and less susceptible to degradation and doesn't fully degrade over these time frames. But recent data is telling us that, in fact, we think this formulation is industrially compostable. So we hope that in the fullness of time that we have an industrially compostable formulation for a pressure-sensitive adhesive. Okay, I'm going to now tell you about the other half of the phase diagram, which is this one. Don't worry, it's not the other half of my talk. I know that's what you're thinking about right now. This will be shorter. You're like, oh my, 90 slides? No, I don't have 90 slides. And so, but that's the high polylactide component. That's not as well studied in styrene isoprene polymers, but we looked at it in these lactide versions because we had basically understood how to do the chemistry. That's what Daniel worked on. And you can ask me about this peak if you'd like, I'll tell you about it. But I'm going to skip over that and say that we know that these things self-assemble like Annabelle's molecules, except now the matrix, the majority component is PLA, and the minority component is PMCl. The one I'll tell you the most about has about 25% PMCl in it, about 75% polylactide. We know that the polylactide crystallizes between the rubbery domains of PMCl. They're not well organized domains. We think they're cylindrical and dispersed through the material. But we know when the polylactide crystallizes by wide-angle X-ray scattering that the domain spacing, the block polymer domain spacing, does not change. And what that means is that it's called templated crystallization. So you can think about a matrix of PLA with some rubbery worm-like things running through it. The AFM helps us understand that better. The light color is PLA and the dark color is PMCl. So this is in a non-crystallized version. Here it's been crystallized, and you can see these little rigid kind of sausage-shaped things are the PLA crystallites, with the darker stuff being the polymethyl caprolactone. If you get the PLA long enough to crystallize, you get what's a heat distortion temperature that's 150 degrees. This is well known in PLA. It's higher than polystyrene or high impact polystyrene. So PLA has a natural advantage in the crystalline state of being hard to deform under a load at high temperature. The tensile properties are impressive. You end up making PLA, which is this black line, which is a stiff, strong thermoplastic, to take this blue one, which is a stiff but very ductile and very tough material. There are the comparison of all the properties of the material. And basically, here's the one I want to point out, two things. One is that it's still pretty stiff material. You could still use it for applications where you need stiffness up to 2 gigapascals, and the toughness is a factor of 80 higher, the tensile toughness. So we get improvement in ductility toughness while retaining high modulus HDT and strength of the material. The kind of classic picture of these tensile bars is clear. This is pure PLA. It breaks under brittle fracture. This is our 75% material, much more ductile. So this thing is extremely competitive with high impact polystyrene in terms of its heat distortion temperature, tensile strength, and toughness. So we think that, like this, plastic cases like on this remote control are probably high impact polystyrene, where you need to withstand dropping it and stuff like that. You want impact strength. So I'm not going to tell you how we studied the fracture mechanism, but basically the fracture mechanism has to do with how these semi-crystalline crystallites deform under load. We think you get what's called coarse slip, which is the crystallites actually breaking up. You might get some stress-induced melting. We have Sachs and wax evidence for this. And you probably get a little initial voiding. That's why the material turns white under tensile. And then you get, we posit that you get fibrillation of the crystallites with these PMCl domains being elongated and coming closer together. We're still trying to understand how these things behave because they're in fact not that tough. Impact toughness is not that high. The impact toughness is higher than PLA, but not as high as high impact polystyrene. So we're still keen, have been searching for it for years, how to make high impact polylactide that retains compostability and renewability. And that's a hard combination. Okay, I'm going to finish my talk now by talking about the end of life. And the end of life is how these things ultimately degrade. I already told you if you add strong base, you can hydrolyze the ester. Nobody is surprised by that. If you put these polyesters in water, Guillaume showed that there's basically nothing happens. Those esters don't hydrolyze at room temperature underwater. But if you add a cutinase, which is an enzyme that, an extracellular enzyme that degrades cutin. You may know cutin, it's a polyester substance on the surface of leaves. That's why water beads up on the leaves. Cutinases can degrade that. So cutinases turn out also to be very effective at degrading our polymer fully. Even at 2 degrees Celsius after a couple months, all the backbone ester bonds are degraded under the action of this extracellular enzyme. So where are extracellular enzymes? They're where microorganisms are. Where are microorganisms? They're in compost. Our materials turn out to be industrially compostable. We tested that by comparing it to cellulose, and absolute biodegradation means how much of the carbon in cellulose, the positive control, is converted to carbon dioxide. And over about 2 months, cellulose is completely converted to carbon dioxide. After an initial lag period here, our materials are almost all fully compostable under this model compost. So in principle, you could make these elastic, PLA is not elastic, tough, PLA is not tough, materials that are fully renewable and industrially compostable and competitive with materials that are sold today. In this paper, we also showed that the polymers accommodate cell growth and the degradation products exhibit low cell toxicity, so we're pursuing biomedical applications of these materials as well. I told you it's important to understand what happens to the molecules. If you polymerize this, you get polymethyl caprolactone. If you add this enzyme, you get hydroxymethyl-caproic acid. So we made C13 versions of methyl hydroxycaproic acid, where the methyl group was labeled with a C13 or the carbonyl was labeled with a C13. If you put these into dirt, the microorganisms in the dirt will use this organic molecule as fuel, as food. And when they convert that into carbon dioxide, every time they make C13 carbon dioxide, there's a shift in the IR spectrum. So we follow the IR spectrum of the headspace. So we know all these carbons, where they end up. And it turns out that 80% of this carboxylate carbon ends up as CO2, and 40% of this methyl carbon ends up as CO2. So we now know how, we predict how these microorganisms, and I'm not a metabolic engineer, so I couldn't talk about pathways to you intelligently, but basically, the bugs eat our molecules and make CO2. They don't make all CO2, so I couldn't tell you where that other carbon is at the moment. It's probably making new biomass. So microorganisms multiply, and those carbons are probably in that new biomass. We need to do the mass balance, which is hard, but we can do it, and others, and this is collaboration with the McNeil group in Switzerland. So the last bit on the degradation is, just last week, NatureWorks, the biggest producer of PLA, came out with a rapidly compostable PLA. Did you see the news? They just came out with it. My students are very interested in this. PLA that composts even faster than it does in industrial compost. Because there's a lot of interest, especially in Europe, in home composting. You got your own home compost bin. Now, some of you are probably good at composting. Others are probably bad, okay? Because you got to keep temperature up, you got to mix it and stuff like that. So home composting has some issues, but people are interested in that. So we tried to look at additives, and this was based on early work by Hyejung on using salicylic acid derivatives. By now using small molecule additives that contain either carboxylic acids or protected carboxylic acids that rely on salicylic acid framework. It turns out that salicylic acid can be biodegraded by microorganisms. In fact, a lot of aromatic compounds go through salicylic acid before their ultimate fate is CO2. So what Eric did was, building on Hyejung's work, was he melt blended PLA with all of these additives one by one, including this protected acid. And when he looked at the PLA, there's no change in mechanical properties of these materials. And he did 0.5%, 1%, or 2%. What we learned, though, was that these things make the PLA, even at 0.5%, much more degradable than PLA itself. So if I look at PLA and I ask what is the weight of the material ratio to its initial weight as a function of time, you'll see that the PLA actually increases in weight in water. This is 50 degrees C artificial seawater. People tell me that seawater is not 50 degrees C. I say, I know, but not yet. It's going that direction. And so you make PLA, and it basically takes up water, and after the peak water uptake, you get rapid weight loss of the material. That's the black data. In all of our examples, we can get up to a factor of 3 faster degradation rate by adding, in this case, 2% salicylic acid without compromising the mechanical properties of the material. If you protect the salicylic acid with this phenyl salicylate, that's the orange data, it behaves exactly like PLA, which means it's clear that the carboxylic acid is important. So the carboxylic acid catalyzes the hydrolysis generates carboxylic acids, which catalyze more hydrolysis. So the autocatalytic mechanism is pretty well established in lactide degradation. We showed that the molar mass goes down as a function of time depending on the additive that you use. And interestingly, and I think this is Cargill's trick, NatureWorks trick by the way, when you degrade polylactide that can't crystallize because of its kind of racemic nature, if you don't use enough of the other enantiomer, you end up getting enrichment in isotactic PLA, and then it crystallizes, and it slows down the degradation rate. So in all of these examples, when you degrade, you actually gain crystallinity from 0 to something finite. But in all of our examples, when you now you multiply that times the amount of weight left over, there's very little bits of that crystalline material, and it all fully degrades way faster than PLA itself. So we think there's a real opportunity to make rapidly degrading PLA by small levels of additives that are engineered to be induce autocatalytic hydrolysis of the esters. And we now have some additives that are even better than these at lower levels. That's enough, I think, for everybody. I tried to talk about the pillars of sustainability. I tried to touch on every part. I tried to acknowledge the students along the way. Feedstock, process, intended use, and end of use. I think that we have a problem with plastic pollution. This is the same issue of science. It's increasing. And I went and when I give this talk to industry, I tell the folks at Toray and Xeon and Ineos and Mitsui, they keep making more polymer every year. So if polymer waste is increasing, one way to stop that is not making as much polymer. And I can tell you, at all of those places, and most companies that I visit, they're laser focused on trying to be more sustainable. And it's largely an issue with economics. And I'll say just a little bit more about that in a second. And how do you all make an impact in sustainable polymers, especially the young people? I argue that it's so important to continue to discover what is possible. We need to know what is possible before we can move to the next, which is how do you make it practical? But the only way to make a real impact is to deploy what is profitable, environmentally, economically, okay? Both. And I think you can do both under the right political environment. At the Center for Sustainable Polymers, we've had 6 startup companies, and I'm the co-founder of Valerian Materials, which is trying to commercialize molecules related to what I talked to you about today. But all of these companies are trying to move from the lab to translation to make an impact in the intersection of sustainability and polymer science. That's why I think they're remarkable. I think we have many opportunities in these molecules. I saw it at CRICT, related molecules at CRICT yesterday. I see it when I read all the wonderful literature about these kind of structures. It's these folks that are making the difference, young folks like are in the room today. This is a current group. I thank all the previous folks. I thank all these folks for continuing those efforts. And then the center paid for it, and that's through the National Science Foundation, resources from the University of Minnesota, and the Minnesota Corn are the farmers in Minnesota who want to sell more corn. Okay, even making plastics. Okay, and so they promote Research and Promotion Council. So Myung, thanks so much, and thanks to all my hosts, Korean hosts, for a wonderful visit. And I hope I left a few minutes here for some questions. I'd love to hear what's on your mind, and I'd love to hear your input and suggestions for where we should go in the future. Thank you so much.